It's live.
Great, thank you. Well, it's a great pleasure to have Almheiri here, and who's going to, looks like, from my perspective, a blast from the past. But anyway, it'll be fun. And thanks, Ahmed, for being here.
All right, thank you for having me. So the official title of my talk is as follows: The Unreasonable Effectiveness of Semi-Classical Gravity Without Microstructure. My talk is going to be mostly about black holes and how smart they tend to be in the semi-classical description. And so maybe a more apt title is The Genius of Brainless Black Holes. And so again, it's going to be about how the semi-classical description of black holes can sort of somewhat shockingly capture non-trivial features of unitary evolution. In particular, I will discuss how the sort of understanding of computing fine-grained entropy in gravitational systems realizes the page curve for an evaporating black hole. I will also argue from ideas of subregion duality used in holography to realize the Hayden-Preskel protocol. And I will justify these ideas from a careful treatment of non-perturbative contributions from the gravitational path integral. That's where I'm going to spend most of my time in this talk. Okay, so to begin, let me review the information paradox. Now, it's sort of a life motto of mine that anything you want to understand about evaporating black holes, you can probably sort of learn it from the eternal black hole. The advantage here is that it makes the discussion much simpler. You don't need to keep track or solve for the evaporating black hole spacetime and worry about what happens at the final moments and so on and so forth. So I'm going to focus on the eternal black hole. Here's the Penrose diagram for a sort of maximally extended Schwarzschild black hole in asymptotically flat space in any number of dimensions. And it was a realization of Hawking that if you include quantum effects into this black hole, you discover that, that it emits Hawking radiation. And in this particular spacetime, it's in equilibrium with radiation coming in from infinity. The way that you compute the state of the radiation in the spacetime was suggested by Hartle and Hawking of evaluating the quantum field theory path integral on half of the Euclidean black hole. This is it's often called a sort of semi-classical treatment. This prepares what is called the semi-classical state of the quantum fields because you're treating them as propagating on a fixed classical background. And this particular state, this particular path integral, the semi-classical state that it prepares is the thermal field double that we all know and love. It can be expressed conveniently in terms of the eigenstates of the Schwarzschild Hamiltonian or the boost Hamiltonian evolving U in Schwarzschild time, as shown here. I will call this state the semi-classical state. To understand the nature of the state, it's sort of most convenient to work with a free theory. So the quantum field theory, let's just take it to be a free field, free scalar field, for example. Then we get this picture that the state describes a collection of entangled pairs across both horizons. So here, the blue interior mode is entangled with the blue exterior mode and the red mode with the red mode. The precise nature of the entanglement sort of gets complicated in general due to gray body effects, which I will ignore in this talk. The claim is that the message of my talk is independent of those details. Now, I claim that this black hole, or this equilibrium black hole, or wormhole rather, has a version of the information paradox. To see this, so you guys see this box, or am I the only one that sees the box? speaker box. Never mind. I think it's just me. Okay, so the way to see the paradox is to compute the entanglement entropy of the outgoing Hawking quanta. You can do that by considering two entangling regions on both sides of the black hole. These entangling surfaces here, let's imagine them as starting at some fixed r, Schwarzschild r outside the black hole, say a few Schwarzschild radii outside, and extending all the way to infinity on both sides. The thing to compute is the von Neumann entropy of these two green regions as a function of time, where both endpoints are moved upwards. I claim what happens in this case is that the entropy essentially grows linearly in time for all time, controlled by the temperature of the black hole. The reasoning is as follows. So this black hole is a static space-time with some temperature T. That temperature T controls the rate of generation of these Hawking quanta, and therefore you expect that it's just going to be linear in time, just T times T. So we have a rate times T. And let me see anything else I wanted to say. Someone might complain. I should say actually first, please feel free to interrupt at any time. So somebody might complain here that when I compute this entropy, this has a UV divergence at the entangling surface. But I'm plotting here something finite. The point is that this divergence comes from entanglement near the entangling surface. So it really has nothing to do with the entropy growth due to the Hawking radiation. In particular, it has nothing to do with the entanglement of the interior with this region. Moreover, this UV divergence is constant in time. And so really the correct thing to do is to just subtract it. It's like subtracting out the vacuum contribution. Okay, so having done that, you find that the entanglement between the radiation and the black hole just grows linearly in time for all time. Now, why is this bad? Because the black hole has a finite coarse-grained entropy given by the Bekenstein-Hawking formula. So that's just twice the Bekenstein-Hawking formula, because essentially you have two sides, two horizons. So it's 2 times the area over 4G Newton. And the important point here is that this gives you sort of a maximum for the amount of entropy that the black hole can support. And this entropy curve in the semi-classical state seems to indicate that the black hole gets more entangled than it has room for. This is often called the bags of gold problem. Okay, so this is the information paradox in this setting. The expectation from unitarity was first sort of analyzed by Don Page, and who said that what you should expect is that the entropy would follow the Hawking curve sort of as closely as possible as it can for the first part of its lifetime. But once it saturates the coarse-grained entropy, it would transition to the coarse-grained entropy essentially. So it would grow and then plateau. So there's a prediction from Page given by the minimum of two quantities, the calculation given by Hawking and the calculation given by Bekenstein and Hawking. Okay, and the point of this talk is to show how the semi-classical description of a black hole knows about this. Okay, and the way that it knows about this is it's going to depend on considering non-perturbative contributions to the gravitational path integral. So now gravity is going to fluctuate, but this sort of immediately raises a problem, which is how am I going to specify a region in the bulk when gravity is fluctuating? There's no meaning to sort of this point to specify this region. The way that this issue can be sidestepped by considering a different model where, I should have included here another reference with, so this was originally with Engelhardt, Morolf, and Maxfield. But yeah, so the model that we're going to consider is a sort of a hybrid model of having ADS space in one region and flat space in the other, where gravity fluctuates only in the ADS region, okay? In the flat space region, the gravity is fixed to just be flat space, and G Newton is 0. Now, the way that we sidestep the previous issue is that we consider entangling regions that are restricted to the flat space regions.
Can I ask already here? So why is this a consistent model?
Why is it not a consistent model?
Why it is consistent?
I'm asking you why should we not expect it to be consistent?
Gravity never turns off. Why?
Good. So more words about this model. Here we have, so we're imagining that we have as I said, an asymptotically ADS gravity theory, where along these lines, we need to specify boundary conditions. What we do is that we specify Dirichlet conditions on the metric, but Neumann conditions on the matter. So while the gravitons in the bulk, they reflect off of this boundary due to the usual boundary conditions that we often impose when we study ADS. But the matter can go through. Okay, so that's the claims that this makes it consistent. Let me see. And to finish the connection with the previous example, there's also a semi-classical state that one can consider for this model, where you perform the QFT path integral on this hybrid Euclidean manifold, where in the white region we have just flat space, and in the gray region we have half of the Euclidean ADS black hole. Okay, and similarly you get some semi-classical state that looks something like this. And everything I said before follows, and you also have this. You also have an information paradox here. I'm not going to rely on holography in this talk, but some intuition from holography sort of can shed light on this model. You can think of this as arising from considering two half-space QFTs in, let's say, d+1 dimensions that are coupled to two d-dimensional holographic QFTs on their boundaries. Okay. In some sense, we've replaced the ADS spacetime with these two holographic systems. So now in this description, there is no gravity. Okay. Just a point of terminology here that is going to be useful for later. You can think of these two holographic QFTs as describing the black hole degrees of freedom, at least as seen from the outside. Okay, why this sort of qualification is here will become clear later. And the flat space QFTs, you can think of them as the Hawking radiation. I should also point out that sort of from this intuition, the paradox gets sharpened, because this growth of entropy interpreted in this picture would be a growth of entropy of sort of between the flat space QFT, the d+1 dimensional QFTs, and the holographic QFTs. But we know that the holographic QFTs have a finite number of states below any given energy, and so the entropy cannot grow indefinitely for all time.
Can I ask a question?
Of course.
So does one imagine that this coupling between the holographic theory on the boundary and the bulk QFT is some kind of, weak coupling, or does it have to be strong coupling?
Good. So in this picture here, the coupling is literally just these Neumann conditions. Okay. I don't have a complete understanding of what this Neumann condition translates in this picture. It might be that it's a simple coupling where you couple local operators here to local operators here. Right. So, right, because a local operator in this holographic QFT creates a local excitation near the boundary. So perhaps it's as simple as coupling a local sort of a local coupling of local operators here to local operators near the boundary of the D+1 dimensional QFT.
So, I mean,
Yeah.
for instance, there are n squared degrees of freedom in the holographic theory. Say if it's n equals 4 Yang-Mills, is one imagining that the system you're coupling it to is just some number of scalar fields that are equivalent to the number of scalar fields that are single trace operators in the bulk of the holographic theory? Or is one imagining a coupling to all n squared degrees of freedom?
I think to get something as simple as this, it might be sufficient to have the former, but I haven't thought too much about this.
Okay, thanks.
Maybe somebody else has a comment. If not,
Can I ask? I still don't understand the picture that you have. So, are we meant to imagine that we integrate over the metrics in the gray region, and then you multiply this with another path integral where you integrate over the QFT over the white region? What is the model? I mean, you have a schematic formula, but is there a more precise formula?
So the full path integral involves a so we have a QFT that lives everywhere. Okay, and the full path integral has a metric variation only in this region. That's how I was thinking about it. So in this region, you have a QFT coupled to gravity, but here I just have QFT on flat space.
So the metric in the white region, does it satisfy Einstein equations?
The G Newton in the white region is 0, and so we just have flat space here. So we imagine joining the metric sort of continuously in some fashion. So we have just flat space metric here, and then we have here ADS metrics that join, well, asymptotically ADS metrics that join smoothly to the flat metric.
But on the asymptotically ADS side, on the boundary, this is infinite distance. There's no metric defined on the boundary. So how is this joining happening?
Good. So this joining needs to be done sort of an epsilon distance inside. So you need to regulate it and cut it off at some epsilon distance inside. So yeah, that's how you should do it.
So sorry, just to follow up on this, your picture on the left looks like, maybe more like a semi-classical picture where you talk about fields and Neumann boundary conditions and that kind of stuff. Whereas the picture on the right looks more microscopic. There you can really imagine you have, CFTs or maybe CFTs with boundaries that look something like what you have on the right. So I guess there's one question is whether you can formulate your Neumann boundary conditions really microscopically or not.
So let me make 2 comments. One is that's still I have not analyzed that problem in detail. Seems like a worthwhile thing to do. Second, these Neumann conditions, remember, I'm sort of imposing them near the boundary, where you can think of gravity as classical, right? So we're imposing Dirichlet conditions here. Second, this is intuition, okay? No claim to having a complete realization of this simple toy model to in terms of things like this.
Sorry,
one final quick question.
Yeah, sorry, maybe this is just a rephrasing of the previous questions. I mean, one thing that one might be worried about if you switch off gravity is that gravity would cause these boundaries to fluctuate. I mean, it would cause the point at which you switched it off to fluctuate. So I mean, maybe the question is if one can define the path integral in such a way that these boundaries are clearly defined even when the metric is fluctuating inside, which may be related to the previous questions. I mean, just because you try and switch off gravity at some point, but gravity causes the walls of the box to fluctuate. So you have a mixed gravity, non-gravity path integral.
But I think it's the asymptotic ADS feature. I think that helps you with that.
But don't you have non-normalizable? I mean, if you thought about it, the matter is streaming out, right? So doesn't the matter cause the metric to fluctuate all the way to the ADS boundary, or not?
No. I haven't analyzed this too carefully, but I suspect not.
But you already said you put it at a kind of finite distance. I think that causes the metric to fluctuate. Maybe I can rephrase it also a little bit using the picture to the right. So in the usual ADS CFT picture where you take the decoupling limit to get the ADS, then the asymptotically flat region is if you see how the decoupling limit happens, you need to turn on your relevant operators on the CFT side. But then you bring back, in a sense, uncontrollable issues with the UV once you put the relevant operators. I guess it's the same, the rephrasing of the same issues.
I think you should probably think of this in the spirit of the calculations that were done originally by Callan Maldacena and Dasan Matur, that you mock up the asymptotic region by saying what operator, and it can be a relevant operator like some scalar field, single trace operator, and you ask what operator mocks up the radiation into the asymptotically flat region from the boundary of the CFT. And so you add to the Hamiltonian of the theory some single trace operator corresponding to that scalar field in the CFT, coupled to the operator that emits from the CFT into the flat region as a source. So you just include some bilinear coupling in the boundary Hamiltonian, and that will do the job of transferring energy from the CFT into the bath.
Maybe I can break in here.
I think all these are interesting questions, but I think I need to keep going.
Just an organizational thing. Two things. One of which, Ahmed, is we carefully put half an hour in between the talks to allow the talks to get extended by lots of questions. So don't worry, you're not going to be penalized. Second thing also is, when you're asking questions, guys, please turn on your video feed. Otherwise, you sound like a voice of God coming from somewhere. We'd kind of like to see your faces. Of course, if you're in your bathrobe, don't turn the video on. But please just try to turn the video on. Over to back.
Okay. So thank you for these really interesting questions. We should discuss them more later. Let me see. So I'm going to keep the discussion general, but the calculation that we actually did, maybe perhaps one in which all of these issues are not raised, is where we consider this in 2 dimensions. So we had JT gravity living in the bulk here, and we had a 1+1 dimensional CFT living everywhere. But I highly suspect that these results generalize. So let me see. Okay, the next thing I was going to talk about is to review how to compute von Neumann entropy and its sort of techniques in systems with gravity. So to begin, let me define the von Neumann entropy. So it's given by negative trace rho log rho, and this is most conveniently computed via something called the replica trick, where you first compute trace rho to the n for integer n. These are the Renyi entropies. And then you take the limit as n goes to 1, and you take the derivative. So you take the derivative, and then you take the limit as n goes to 1. So you have to continue it. Let me sort of describe how this happens for a QFT without gravity to begin with. So suppose we have a pure state, say the vacuum, prepared by the Euclidean path integral. So here, this lower half can be thought of as the ket, the upper half as the bra. So this prepares the density matrix 0, 0. Now, suppose we divide our system into a left and right side, and we want to compute the entropy of the right. So to do that, we need to trace over the left side degrees of freedom. That trace isn't what it does is that it allows the Euclidean path integral to smoothly connect along the left-hand side. And then you have a Euclidean path integral with boundary conditions, I and j. I and j represent the sort of matrix elements of the density matrix of the right. Okay, so this is all standard. To compute the Renyi entropy, one needs to consider n copies of this density matrix, and then you have to multiply them together and take the trace. Doing this procedure is the same thing as joining the, considering first n replicas, and then joining them in the following way, in this replica symmetric way, where the I index of one sheet gets glued to the j index of the other sheet, and so on and so forth. And to compute trace row to the n, you simply have to compute the path integral, or you have to evaluate the path integral of this quantum field theory on this replicated manifold, which I call Rn. This is sometimes sort of conveniently expressed in terms of what is called the branched cover, where these sort of different sheets are flattened, and the different sheets are identified by going through this branch cut, okay, which ends at this branch point. The most precise techniques for computing this path integral is sort of introduced by Cardi and Calabrese of computing writing this Renyi entropy as a correlation function of twist fields, where this twist field is the thing that implements this branch point and branch cut. It's located at the branch point. And it has nice properties. It transforms like a primary operator and so on and so forth in 2 dimensions. And the idea, sort of having known what this correlation function is, you can read off the entropy by taking the limit as n goes to 1, and then just extracting the exponent. Okay, this statement here is really the same as the statement here, that you take the derivative and so on. Okay, so that's how you compute entropy in systems without gravity. What about with gravity? Things are much more interesting here. So suppose you have a QFT in asymptotically ADS gravity, where you're allowing everything to fluctuate. Okay, gravity as well. And suppose we consider a path integral in which which is sort of highly peaked, sort of about some semi-classical saddle. Okay, so here I'm sort of representing some saddle, some Euclidean saddle, where if I was to cut it along the red line and then continue to Lorentzian time, it would be some nice semi-classical Lorentzian geometry with quantum fields propagating on it. Okay, suppose I give you the state. Now we want to compute entropies of regions in this theory, but again, we don't have that many options. We can't consider regions in the bulk because gravity is fluctuating in the bulk. And so it seems like the only thing that you can compute the entropy of are the boundary degrees of freedom. Okay, so I'm going to sort of follow the same procedure here and say that I want to construct a density matrix of the boundary degrees of freedom. What that imposes, or the way that that's done, is you need to trace out the bulk. Tracing out the bulk is like evaluating the full path integral of the bulk theory subject to these boundary conditions. Okay, so this thing prepares for you the density matrix of the boundary degrees of freedom in this theory. Okay, I'm being schematic about what these boundary degrees of freedom are. I don't want to appeal to holography, although maybe everything that I'm saying here only makes sense in a situation where this bulk theory is, type 2B string theory in ADS5, process5, or some other top-down constructions, where you'd understand these I's and J's as, where you'd understand the boundary degrees of freedom as the holographic CFT. But I don't want to appeal to that yet. Okay, to compute the entropy of these boundary degrees of freedom, you need to replicate the system. So you need to replicate this density matrix, and you need to identify it in this way. Then you need to evaluate or consider the path integral subject to these identified boundary conditions. Okay, here these identified boundaries are represented here by this red cross here. That's supposed to be the identification. And the thing that we're instructed to do when evaluating this path integral is consider all gravity configurations that join sort of smoothly to these boundary conditions. So what ends up happening is that gravity naturally extends this the branch cut that was in the restricted to boundary into the bulk, right? So you want to get a smooth spacetime, you need to have a picture like this, okay? And by virtue of these boundaries being identified cyclically along the replicas, the bulks are also going to be identified cyclically along the replicas. One point here is that in this talk, I'm only going to consider replica symmetric configurations, okay? And this is sort of a nice thing about gravity, is that it's sort of very hospitable. You knock on its door and it invites you in, okay? That's a feature of gravity. And let me see. So any question right now at this point about the analogy between these two cases and how gravity sort of does it for you? Okay, I'm going to talk about equations now. Let me see. So in evaluating the Renyi entropies here, what you're evaluating now is the full QFT plus gravity path integral, but now evaluated on these configurations. And the simplest way to do this is to consider the saddle point contributions to this path integral. Okay, so it's going to look something like this, where you're going to have so it's going to be weighted by so this is the gravity path integral weighting, and here you have the path integral of the QFT. I should have written QFT here. So the Z is the QFT path integral on the background GN saddle. And the thing that determines these saddles are the equations of motion, which are just these so Einstein's equations, sourced by two terms. One is a term coming from the branch point. So here I'm thinking of the equation of motion on the branched cover. This branch point here, you have a conical excess. And so you need to insert a cosmic brane to source this conical excess. Second of all, you have energy generated by the twist fields, if you will. Okay. And this is the equation you need to solve. Now, one comment I need to make here is that this T here it's sort of an expectation value of the stress tensor coming from the quantum fields. And therefore, the sort of defining or sort of a requirement that this saddle point is sharp, that it's actually a saddle point, or rather that it has small fluctuations, is that this T here has small fluctuations. One way to ensure this is to have your matter theory in the bulk have large number of degrees of freedom. So in the actual calculations that we did in 2 dimensions, we considered a CFT with a large central charge, but still much smaller than 1 over g Newton. Okay, so that's just a side comment for those that might worry about how rigorous this is. Okay, the point that you should take away from this equation is that for n not equal to 1, both of these source terms are non-zero. So the gravitational solution that you have in this sort of branched cover spacetime is very different from the n equals 1 solution. Okay, but thankfully, to analyze this problem and extract the entropy, it turns out to be sufficient to work near n equals 1. So from now on, I'm only going to consider the regime where n is close to 1. If you work with n close to 1, one observation you make is that the QFT path integral becomes the path integral again on the branched cover, but where the metric where the metric you can use is the original n equals 1 metric. Okay, so this is the original space-time that we started with. And then when you take n goes to 1, this implies that the matter entropy that you will compute will be the semi-classical entropy of this region sigma x, because here's where you have the branch cut, in the original semi-classical state on the original geometry. Okay, so this is an important point which perhaps I'll refer to later. Then putting everything together, you find that the Renyi entropies are, again, I'll put back the sum over saddles. Here's a semi-classical entropy piece, but you also get an area piece. This area piece is the thing that comes from the gravitational action. And you should really think of it as coming from the requirement that when you go to the replica manifold, that these fixed points of the replica symmetry, that the space-time is smooth there. Okay, this is really the same argument that led to the area term in the Gibbons-Hawking calculation. And one more thing to emphasize is that in this limit of n near 1, the action became simply the generalized entropy. Okay, by virtue of it being a saddle point, small metric variations should vanish, and moving the location of the surface x can be thought of as a metric variation. And that's the thing that gives rise to the extremality condition for the generalized entropy. Okay, so this is sometimes called the it's a quantum extremal condition, because you're extremizing geometry plus quantum corrections. But I'm just going to say regular extremality condition. So the takeaway from this slide is that in order to compute the fine-grained entropy, you don't need to go through this entire procedure of going through the replicated manifold and so on and so forth. You derive the following formula. There's a formula you can implement on the original geometry, where you take the generalized entropy, the area plus the entropy semi-classical, and you extremize over the surfaces. The different extrema are the different saddle points, and therefore the one with smallest value of generalized entropy is going to dominate. And that's the thing that gives you the minimality condition. So the relevant surface, the thing that computes the entanglement entropy of the boundary degrees of freedom here, is the minimal extremal surface. That's a bit of a mouthful. So instead, I'm going to call the minimal extremal surface the extremist surface. I'll leave it up to you how to spell extremist. Okay. Let me make 2 comments before I take questions on this. So one thing, these two comments are sort of applications of this formula that might have been missed in this sort of derivation. First is the possibility of having no surface. Okay, this is the case where the branch cut at the boundary gets pushed in all the way into the bulk and just cuts the bulk spacetime in two. Okay, in this case, the entropy of B is just going to be the semi-classical entropy of the region sigma. Okay, so this is the trivial surface. Note that this trivial surface is automatically extremal because there's no x to extremize over. The other possibility, the more interesting one, is the possibility of disconnected regions, which have now been, which now are sort of called islands. And this is the idea that you can have these regions sort of deep in the bulk that are also connected in this replica symmetric way. And from the branch cover perspective, that corresponds to this sort of nucleation of two branch points and a branch cut connecting them. This region I will call sigma island. In this case, the entropy of the boundary degrees of freedom is the sum of the areas coming from x1, x2, and x, plus the semi-classical entropy now of the union of the island region and sigma x. Okay, any questions about this?
I have a question.
Yes.
So I think you said you assumed that the bulk is replica symmetric. So how important is this?
Good. And in the discussion later of the page curve, it's so I was not able to, I don't think anyone was able to compute the effect of non-replica symmetric saddles in this setting. However, there is a much simpler setting that was analyzed by the Stanford group of just JT gravity coupled to a end of the world brane. And what they find is that the non-replica symmetric saddles, they smoothen out the page curve. So I will refer to that later. Okay.
And a related issue, so you're also assuming that the formula is analytic in n, so you can take the limit n to 1. I mean, there are in quantum field theory, there are counterexamples, but will this play any role here?
I was assuming that n can be made into a parameter that can be continued. That's definitely an assumption. Okay. Now, so now we have the formulas. Let's apply them to our example. I should say that when I first discussed the paradox, it was a paradox about computing the entropy of the Hawking radiation. But now, because we have, we can sort of split the degrees of freedom into the black hole degrees of freedom and the radiation degrees of freedom. And what I mean by that is just in terms of the regions in the flat space region. So here, what I call the black hole degrees of freedom are those that start at the ADS boundary and extend a little bit into the flat space region. I'm imagining this is a small epsilon thing, but I just sort of in the calculation, I do this just to regulate things. Okay, and so we find, so now let's just apply the formula. One contribution comes from the trivial surface, where the branch cut extends into the bulk and slices it in two. In this case, the entropy of these boundary degrees of freedom, B, is just given by the semi-classical entropy. Okay, and it's just going to keep growing in time for all time, basically because it captures the entropy of the interior Hawking quanta. Okay, and it just keeps piling up. The other contribution comes from the non-trivial surface, where the branch cuts end at some branch points in the bulk in this fashion. Let me just make a comment that even though I drew this as being present at t = 0, it's actually in general not present at t equals 0. So you should think of this saddle point as a complex saddle point, which becomes real after some time evolution, after some Lorentzian time evolution. So you need to time evolve by a few thermal times for this to be a real saddle point. That's a subtlety which is not too important for us. But in any case, in this case, the entropy of B is going to be the areas of these surfaces plus the entropy of the union of sigma x1 and sigma x2. Okay. An important point here is that x1 and x2 are extremely close to the event horizon of the black hole. They're sort of an order of Planck length near the black hole horizon, if you will. The value of the area there is very close, is up to order 1 corrections equal to the area of the horizon. And so the answer that you get from this contribution is precisely the coarse-grained entropy because of the area term. The semi-classical entropy piece is very small. It doesn't contribute. And now putting sort of everything together, the entropy of B is the minimum of these two contributions. First, it's going to be given by the semi-classical answer, the red curve, and then it transitions to the blue curve. So the minimality condition gives you the black curve. And as I said before, the non-replica symmetric saddles, what they do is that they smoothen out this transition. Okay, so that was the black hole degrees of freedom. What about the entropy of the radiation? So now you need to consider a region outside like this. So that's a branch cut in the flat space region as shown. There's the trivial surface, which just means the no island surface, where the entropy is just a semi-classical entropy of these green regions outside. So note that this is going to be equal to the entropy of, it's going to be equal to the trivial surface contribution of the entropy of B shown in the sort of 2 slides ago. And again, this gives this ever increasing entropy because it just captures the Hawking radiation escaping. Okay. Then there is the more interesting contribution, which is the non-trivial island contribution, where you have the emergence or the nucleation of these 2 branch points and a branch cut in the ADS region due to the branch cuts in the flat space region. And as a function of time, as these endpoints are taken forwards, the island moves upwards along some trajectory as shown. Okay. And again, x1 and x2 are near the horizon and so on. And it's just equal, it's precisely equal to the entropy of the black hole degrees of freedom in for the non-trivial surface case. And again, so you get something like this. Putting everything together, you get the page curve. Now we understand why the entropy of the radiation doesn't increase for all time. The reason being is that when you compute the entropy of the radiation, it includes an island in it includes an island that contains the black hole interior. Therefore, both modes contribute to the entropy of the radiation. By that I mean they purify each other. And so that's why the entropy doesn't keep growing. And just as an emphasis here, the reason why the transition happens is, or rather the thing that allows the transition to happen is that it becomes convenient to include the area term. Right? The area term is a 1/g Newton term. It's a very huge contribution. You can ask, when would this ever be convenient? Well, it would be so when the entropy, when the semi-classical entropy becomes of order n squared, or of order 1/g Newton, and that's when the transition happens. Okay, any questions about this? Okay, the final thing I'm going to talk about is the Hayden-Preskel protocol and the entanglement wedge. So the entanglement wedge is the causal development of the region appearing in the entropy formula. So if you want to compute the entropy of some region R, there's a sigma x appearing. The causal development of the region sigma x is the entanglement wedge. And there are various results from sort of various results when discussing holography, saying that the entanglement wedge is the answer to subregion duality. So the statement is that sigma x is dual to R. Everything, well, information about sigma x can be reconstructed from R. We can discuss later how much information in sigma x can you reconstruct in R. That's a subtle question we can talk about later. The point here is that there's an evolution to the entanglement wedge going from before the page time to after the page time. Before the page time, the entanglement wedge of the black hole degrees of freedom includes essentially the this causal diamond in the bulk. The entanglement wedge of the radiation is just the radiation region. But after the page time, the entanglement wedge of the island now contains the interior. So the interior now is dual to the radiation region. And so this gives a really crazy answer to the question of, although maybe not that precise, it's still a bit vague, but it's an answer to the question of how does the information escape the black hole? It turns out that the information doesn't escape the black hole. You don't need it to escape the black hole for it to appear in the Hawking radiation. But I guess in the terminology that we're using, the information escapes the black hole as seen from the outside, right? Those are the degrees of freedom B. And finally, this gives a realization of the Hayden-Preskel protocol, where which was a statement that after the page time, if you throw some information into the black hole, it appears almost as fast as it possibly can. The title of their paper featured black holes as mirrors. And what you find here is that the information you need to wait to get the information out is precisely what they predicted from sort of quantum information theoretic grounds of studying random circuits and so on. And the information, the time is precisely the scrambling time. So this is sort of, it's sort of how much time in the past you have to, it's how much time in the past you have to throw in the information so that it appears now. And the answer is you need to wait the scrambling time. And it's really crazy that this semi-classical analysis captures this time accurately. Any questions?
I'm very confused, actually. Hi, I'm Yosif. I'm very confused about this this thing, because on one hand, I would say, okay, if I take a mega big black hole and I throw a computer into it, the scrambling time is like the crossing time times a log. But the amount of energy which this mega big black hole emits, because the temperature is very, very low, the amount of energy which emits is going to be infinitesimal. And I can make this thing to be infinitesimal. Now, the question is, how can this have the information in my big computer using, like, you know, an epsilon of energy? You cannot have information without having energy out.
But Joseph, this time also depends on beta. So when the black hole is very, very large, well, actually, in the case that you were describing, larger black holes have smaller temperature, and so larger beta. So,
but still, I think, I mean, if you look at the amount of Hawking radiation and, you know, amount of energy which goes out in the scrambling time, that amount of energy is going to be, I mean, I think it decreases with.
Yeah, no. There is a refined. Sorry, yes, you're right. There is a refined formula that depends on the energy of the matter that you throw in. So it gets extended for larger things that you throw, you need to wait for a longer time.
Mhm.
But also, I am also making the assumption here that you need to collect a number of quanta, which is slightly larger than sort of the amount of matter that you threw in.
Mhm. Okay. Ah, this is the assumption. So in a sense, this formula cannot be taken in the limit when the black hole becomes very, very cold.
So operationally, if I've got a black hole that was 10 to the 9 solar masses, it's now evaporated down to 1 solar mass. So it's very, very, very old. And I give you a 1 solar mass black hole. How do I tell the difference
Between what and what?
between a black hole that started out as 10 to the 9 solar masses and is evaporated all the way down to 1 solar mass versus a newly minted black hole? What's the microscopic difference? I look at this thing. What's the difference?
Can we discuss this later?
Certainly, yeah.
But if you're allowed to do very complicated operations or not?
I'm an astrophysicist. I'm going to put, watch accretion disks and, I want to see what what the difference is. I think this is, as Ahmed said, it's probably best left for the discussion this afternoon.
Okay, or maybe the discussion after the talk. But let me, so this is all I had to say. Let me just make some final comments. Might ask, does this resolve the information paradox? Okay. Now, my take on this is that there are at least 3 things you can mean by the information paradox. One is understanding and accounting for all the microstates of the black hole. This discussion doesn't add to that at all. The next question is, or the next interpretation you can have, is finding the unitary S matrix for the black hole. This presents some minor progress on that, just via the entanglement wedge reconstruction ideas, but certainly nowhere near a full understanding of this. And the third point is reproducing the entropy curve consistent with unitary evolution. And that's what this calculation does. And the thing that sort of feeds into this is sort of what I have on the right-hand side, which I've sort of titled "The Mistake," because everyone keeps asking what was Hawking's mistake, in quotes. And it's the idea that treating the, at least in our model, the state that Hawking considered when computing the entropy was the semi-classical state, where in the gravity region, you simply put in the Euclidean black hole. But the actual state of the radiation outside here depends on the gravitational region. Okay, that's a statement here. The preparation of the state it's certainly dependent on the path integral included the gravity region. So you should take that full path integral into account when computing the properties of this state. And the thing that we computed was the entropy, and we saw how it cared about different configurations of the path integral other than the semi-classical Euclidean black hole geometry. And that's all I had. So here's just here's a summary. So we derived this gravitational fine-grained entropy formula and showed how it produces results consistent with unitary black hole evolution. And this comes from a careful treatment of the gravity path integral, revealing these non-perturbative corrections to the Hawking analysis. And I also gave a manifestation of the Hayden-Prescott protocol in terms of evolving entanglement wedges, and some open problems. I'm sure there's more, but this is all I can fit in before starting this talk. The first is that you might complain that this is just semi-classical analysis. I would completely agree, and I would be very interesting to understand what is the microstructure or state interpretation of these results. But nevertheless, I really think this is a really important result. I really think that had Hawking found this result in his day, he would not have said, well, because we don't have a microscopic interpretation, this is a paradox. He might have called it a puzzle, but it seems that the entropy evolution paradox is not a paradox anymore, but there are other puzzles to understand the interpretation of the formulas and so on and so forth. And there are some issues here. Oops. some issues about wormholes, when to include them, when to not include them, averaging, blah, blah, blah. I have no comments to say about that. So let me stop here. Thank you.
Thank you, Ahmed. That was great. So very nice talk. So Emil's got his hand up. So I guess he gets the floor first.
Yeah, so I wanted to come back to this question about the Hayden-Preskill protocol. So, and it ties into the discussion we were having earlier about exactly how you couple the gray region to the white region. So if the coupling of the gray region to the white region, so again, if I'm thinking about, n equals 4 super Yang-Mills, I have some large N gauge theory in the gray region. The white region is your favorite, bath that you're going to couple it to. And if I imagine that the way they're coupled is that I couple some single trace operator, some relevant operator corresponding to coupling some light mode in the bulk of the gray region to the bath, then that's some kind of order 1 coupling, not an order n squared coupling in terms of what degrees of freedom couple to what other degrees of freedom. And so if I'm throwing in some bit into the black hole, it somehow has to, once it gets into the black hole, the usual picture was, okay, there's some scrambling, some fast scrambling among n squared degrees of freedom. And that's, remarkable. And somehow we have to extract that scrambled data by some tiny coupling at the boundary to the bath. And I'm confused about how that works. If there's so somehow the island is evolving. Mm-hmm. And the island involves transferring entanglement between or data between the island and the bulk seems to be a process that needs sort of n squared degrees of freedom mixing with each other. Whereas the transfer that's going on at the boundary seems to involve order 1 degrees of freedom.
So I think this is a function not of how the energy is transferred from the holographic QFT to the path QFT. I think that energy transfer can be very simple, but the important thing is whether the holographic CFT itself is scrambling. That's what I would say.
Let's see, the less degrees of freedom you have, the more stretched that green island is, right? The bigger the time you have to go into the past.
Mm-hmm.
So that's where the number of degrees of freedom come in. I mean, how many radiation versus black hole degrees of freedom you have.
So have I changed the Hamiltonian coupling the bulk and the radiation by a large amount in order to execute this fast transfer? I mean, is the Hamiltonian of the system differing dramatically from the Hamiltonian of ADS-CFT as far as the gray region is concerned?
I think that the smaller the coupling, the more stretched the green region will be. I'm just telling you what the answer will be, but not.
I think you just
any interpretation has to take this into account.
I think you just so if the coupling was small between the boundary and the bath, then you would just need to wait for a longer amount of time, is a statement. So I mean, this effect from the bulk perspective came about because the boundaries became, in some sense, maximally entangled with the baths.
Right. So sounds like you're saying that if I want the transfer to happen within the scrambling time, then somehow all n squared degrees of freedom of the gray region have to be coupled to the bath. I can't just do it by couplings of single trace operators.
No, it's not. If you have only one field coupled, then it's the scrambling time. If you have more fields coupling, it's slightly shorter than the scrambling time, but only by a log of S over the number of fields that you.
Nick, you're muted.
Thank you. Costas, you're waiting to ask a question. I don't know. We should.
Yes, yes, I do.
Go for
Is it possible to run the same argument for the D1, D5P non-extremal black hole, in which case there are not going to be any of the issues we have been discussing? You have a asymptotically flat region and becomes the ADS black hole as you go to the near horizon region, and none of the issues we discussed earlier would come in.
Yeah, I suspect so. Although I'm not an expert in that model, but yeah, I don't see why not.
Well, it looks a cleaner setup. Why hasn't been done? I guess that's the question.
I guess cleaner is in the eye of the beholder.
But one, I mean, the coupling at the boundary, you go from a metric which is infinite to something which is constant. That looks very severe. It's
well, but it's the same thing that is happening in this model, right? So
no, in this model, this is what is happening. But in the other case, there is a smooth transition.
Well, but as Ahmed said, that you regulate it, and then you get this, and it turns out that the physics doesn't depend on the regulator.
But is it
in the D1, D5? This how much? I mean, roughly the size of this regulator has to do with the depth of the throat in the D1, D5 system. So the longer the throat.
But suppose you have a small, you put a small regulator, let's say epsilon, which is, you know, 10 to minus 3. Then the metric at the boundary would be 10 to minus 3. The Minkowski metric, the metric on the other side will be 1,000 times bigger. It's the smaller
the metrics are continuous. The metrics are continuous. I mean, when Ahmed said it's just the flat space metric, I mean, yeah, it's up to a factor that you match them continuously, and because we're dealing with a CFT, it doesn't matter. This factor doesn't matter, but this factor is also present in the ordinary D1, D5.
But in that case, you know exactly what is happening. You turn on irrelevant operators. So I think I wouldn't agree that it doesn't matter. It's you know, the linear deviation from the decoupling limit is okay. In the case of the ADS 5 crosses 5 is a dimension 8, and there is a similar irrelevant operator in the case of the ADS 3.
Yeah. The whole mechanism of how you couple from ADS to flat space. Of course, once you have an explicit gravity solution, you can describe it in detail and discuss these operators and so on. But for the physics that Ahmed was discussing, it doesn't matter.
I guess this is what is not clear to me is why it doesn't matter. But I guess we can discuss later.
Because you can just apply the island formula, the entropy formulas, on the original geometry.
But the question is back why the island formula is the correct formula, right? I mean, we in a sense. Of course, if you accept the island formula, then okay, it wouldn't matter. If you take as evidence the result that you got, then okay, I agree.
Okay. Any other? Let's let somebody else in from it. Anybody else got questions? Samir, maybe you want to chip in at this point. No? Oh, Stefano Antoni. Go ahead.
Thank you. I just wanted to ask, do you think that the fact that what allows purification of the radiation is an island which involves the interior of the black hole is a hint that in a microscopic realization of this process that allows information to escape, you would have a violation of locality?
So this definitely does say that the theory is non-local, that you can due to non-perturbative gravity effects, you can do something on the radiation and affect something deep inside the black hole. So that's definitely a feature of this. I guess one comment is the thing that you need to, the kind of operation you need to do on the radiation to actually exhibit this is actually extremely complicated. So that's one comment. You know, it takes a very long amount of time and so on and so forth, etc. So it's not clear that you would actually see these. It's not clear that you would actually have causality violation. We tried to consider situations where we tried to end up with something like this, like causality violation, by decoupling the ADS region from the flat space and so on. But gravity was always too smart for us. It always sort of precluded any causality violations. Although I wouldn't say we proved that there are no causality violations. The other comment, I don't know if this is also something that you were sort of hinting at. This picture is it sort of gives you, well, it gives you a semi-classical picture of how to get the information out without replacing the black hole by some microstructure at the horizon, cutting off the space-time inside. And so it raises a sort of a good question for discussion. Do we need these microstates that end right at the horizon to for unitarity, or is something like this sufficient? It's a question for the audience.
So this is Samir. Could I just ask a little bit about this picture you have on the screen?
Of course.
So you said, talked about getting information out, but it seems to me you actually didn't get it out. Whatever was inside is still inside. Somehow what is inside is being defined as also being part of what you should think of as being outside. If you have to get it outside, you will need, as the previous person was asking, some non-local interaction which will maybe move it outside. And that interaction is not yet drawn in this picture. Am I correct about that?
Yes, you're correct. I didn't show it here, but in a very simple explicit model considered by the Stanford group, they showed how if you throw in some information inside, you can act with an operation in the radiation which extracts it. The thing that it does, roughly speaking, is that it creates a wormhole between the radiation and the interior that allows you to access the information behind the black hole horizon. So that's sort of what the calculation looks like to prove or to show that the radiation is sensitive to the information behind the black hole horizon.
Okay, very good. So you would say the black hole there is quite a different object from a piece of coal or a normal star or a planet. That is, when a star radiates and the radiation is entangled with what is inside and so on, everything is like here in terms of entanglement. Let's say a star evaporates past the halfway point. And now if you do something outside, will it also create a wormhole into the star and pull something out? Or I guess you're saying there the answer is no. This is something peculiar to the black hole where these novel quantum gravity effects have now come up, and a piece of coal would not have this. Is that correct?
That's correct, because it's, and for the piece of coal, you're always in this region. It's always the semi-classical entropy that computes the entropy. But for a black hole, there's the island, or there's a non-trivial surface, whatever you want. There's this other saddle point in the gravitational path integral that becomes important. That's another way of saying it. So for a piece of coal and a star and so on, you only have this. But for a black hole, you can have this.
Okay, so maybe one final question, just so I could understand this. The wormhole I can be as far as I want from the black hole, and the efficiency of the wormhole is the same. It's not like if I go very far, it becomes more difficult to make the wormhole. The wormhole somehow always has the same size or action or whatever. Is that correct? It doesn't matter whether I am distance m cube or 10 m cube from an evaporating black hole. I can still get in there and extract the information with the same difficulty. Is that right?
I'm not sure what is meant by same difficulty, but it might be that the longer you wait, maybe, it depends on the situation, that the kind of operation you do on the radiation might become more complicated. But if you, nevertheless, there is a procedure you can implement which would probe the interior and would probe it with the same sort of success probability, if you will. But let me just make it even more troublesome. You can have a black hole that evaporates away completely. So just imagine the back of your head, the completely evaporated black hole spacetime. If you collect all the radiation in the far future, once the black hole is gone, you can do an operation on that can probe the interior of the black hole in the far past. Okay, that's how crazy this is. And maybe in the panel discussion, I can bring up the picture, or maybe Juan already has that picture, and we can discuss that case.
Thank you.
Stan Nicholas has been very patient, and he's had his hand up. Go ahead, Stan.
Thank you. I'd like to ask the following question regarding precisely the figure about the evolution time of the entropy. No, it was just that's right, because I was just wondering what about this cusp here, because one would naively think that this should be a sort of smooth curve, and therefore the fact that there's a cusp means that there's something that's been forgotten. Is there any way to see in the framework of this calculation what's been forgotten?
Yes. So there is indeed something that has been forgotten. I mentioned this in the talk. It was it's now I'm going to go back in this calculation.
Mm-hmm.
We only considered replica symmetric configurations.
I see.
But you can consider configurations where, so here, if you look at this wormhole contribution, you can have wormholes that connect, say, this sheet and this sheet, but not this sheet.
Mm-hmm.
So these are non-replica symmetric configurations. And in a simple model studied by the Stanford group, the thing that they do is that they smoothen out the page curve.
So this curve will be smoothed out by the contribution of of configurations that break replica symmetry.
Correct.
Oh, thanks.
Any other questions? I have a brief comment. I said this before, but let me rephrase it. Maybe it's appropriate to the afternoon discussion. But if I look back on what we knew 30 years ago, we knew that the interior of a black hole contained all the the entangled pairs that would need to purify the Hawking quanta, and so there was this problem way back when that basically what you need to purify the Hawking radiation is inside the black hole, and somehow that's got to get out. It's buried inside it. Now, what this calculation looks like it's doing is saying, look, suppose we put in a little bit of knowledge about Renyi entropies and how we calculate them, and perhaps with holographic insight. And then what we found is there's this thing you call the island, which is in some sense some semi-classical instantiation or some semi-classical embodiment of all that stuff we need to purify the Hawking radiation. But at the end of it, what we've learned is a little bit more about the stuff that's inside the black hole, but we've learned very little about how it actually gets out. And so while it's a nice calculation that shows a little bit more, if you want to rescue the unitarity of quantum gravity in 3+1 dimensions, this stuff has to get out somehow, and you sort of build it in from the outset by saying, okay, I'm going to use these entropy formulae. So have I really learnt more than what I knew a long time ago?
I think you have. So what you're talking about right now is point number 2.
Yeah, I think I'm probably pissing and moaning about the fact you haven't answered 2 and 3. I think that's really what's going on. Oh, sorry.
No, I haven't answered 1 and 2. I've answered 3. So it's a statement that it's because the techniques that I discussed were only they are useful for a limited set of questions. They can't tell you, they seem to not be able to tell you the details of the outgoing state. But what they can do for you is compute the entropy, and somewhat magically, it was able to give you the quote unquote the right answer in a semi-classical language. It's saying you can compute the entropy by first assuming that the state is semi-classical and provided that you use a new set of rules. It's almost like gravity doesn't trust us with the actual mechanism for how information goes out. It's like, here, just do this, and you'll be satisfied with this answer.
I think we should probably leave the following up on that later this afternoon. Any other questions more specifically about the talk or? Okay, so we'll take a 10-minute break and then Juan will pick up. Thank you very much. That was fantastic, Ahmed.
Thanks a lot.
Thank you.
I'll leave the YouTube recording going, so people who want to discuss everything will be recorded. We'll have the same YouTube link for both talks. So I'll leave the YouTube is going to be on. Maybe it's better if I mute everybody, and like that we know that people don't.
No, it's okay. Just leave it on, Joseph.
Okay.
Let me try my screen sharing.
Juan, are you doing it from your iPad or just from your?
No, this time I'll do it just from the computer.
Okay, so you've got the authority of a co-host.
Mm-hmm.
Great, we can see it.
Works.
Yep.
Can you play it and make sure that the mouse works?
Yep, perfect.
You can see it?
Yep, everything's good.
Okay.
Okay, so I'm going to take a 5-minute break.
Yeah, it was a very nice talk, Ahmed.
Thanks. So what did you settle on for the panel?
More or less what I sent you. Yeah.
Okay. Okay. Very good. Very good. Yeah, I'm going to think about what I'm going to talk about now.
Well, you're. It's good. You can address the questions that were asked.
Essentially. Okay, I look forward to your talk.
I guess one thing one could say is that it's true we don't know how to calculate the S matrix, which would allow us to compute any observable.
Mm-hmm.
We somehow know how to compute one observable, which is the entropy roughly, or the Renyi entropies.
Mm-hmm. Yes.
And the lesson is that the properties of the interior contribute to the computation of this particular observable. I mean, for the radiation.
Mm-hmm. Yeah. I forget, in your email, did you say you were going to talk about the closed universe example?
Yeah, let me show you. Yeah.
Okay. Okay.
But a little bit. I mean, it's just one particular example. You might say a little more.
Okay, I think we're back. Joseph, you there? I guess.
Yes.
Excellent. Okay, so we're recording. Fantastic. So it's a pleasure to have one to talk to us now. What seems to be a slightly different tack, but I'm sure it'll be extremely interesting. It's on entropies in 2D cosmological models. Over to you, Juan. Thank you.
Okay, thanks for the invitation. Can you hear me? Well.
Yep, no problem at all.
Okay, good. So I will be talking about some work that is ongoing that we're doing with Yimin Chen, who's a graduate student at Princeton University, and Viktor Gorbenko, who's a postdoc, was at the Institute and now is at Stanford. So the idea is similar to what Ahmed was talking about. So we will compute some fine-grained entropies using the RT formula and its generalizations with the goal of getting some insights on cosmological questions. This will lead us to some interesting sort of bracket wormholes or cosmological wormholes that well, I think have interesting consequences. So the general philosophy is also to explore these questions using the RT formula and its generalizations, which we have written here, and Ahmed just explained how to use it. We'll also include islands and this type of disconnected contributions. And part of the goal is to apply this to simple cosmological models. And this formula is best applied when there is a region where gravity is not important. So for example, in the case that Ahmed discussed, there is this flat space region where gravity is not important. There we can define regions and we can understand whose entropy we're computing. And this entropy is important because it gives us valuable information about the map between the quantum microstates or the microstates that appear in that region where there is no gravity and space-time geometry. So we will discuss a simple toy model, and the simple toy model is very closely related to what Ahmed discussed. So we'll have a toy model where we have the zeta space with gravity here in this region, the green region. And then in the future, it will transition to flat space with no gravity. You can view this as a kind of model of inflation where we have inflation for a while, and then inflation ends, and then we go on to a slower FRW evolution, and we will neglect, of course, the expansion of the universe in this yellow region. Will approximate it just as flat space and with no gravity. So that's, of course, it would be an approximation to an actual cosmology. It's a toy model where the transition is very sharp and we have very different evolution. And we mainly talk about the case of 2 dimensions where we will have JT gravity. And so we'll have JT gravity in the green region coupled to a 2-dimensional CFT. And then as inflation ends, we'll have the 2-dimensional CFT living here in the future, okay? And these transparent boundary conditions, which maybe cause some consternation in Ahmed's talk, certainly would seem to be a choice there, here are also very natural. Of course, they are also natural in the case of 4-dimensional, let's say some d-dimensional black holes that we are approximating using this toy model. Okay, so this will be the main objective of the talk. But first, we will take a detour. So we'll discuss a different model, a different setup that will give us some intuition for how to treat this other problem we just discussed. And we in our research, we first thought about this model, we got confused, and then we solved the confusions by looking at this other model. Okay, so now first let's recall a toy model, a black hole toy model. This is just what Ahmed discussed. So ADS2 gravity with a CFT2, and then flat space with no gravity, and again, the same CFT2 with transparent boundary conditions for the CFT2. Now, in this case, the advantage is that we think we have duality where we think that the full complete description of the left-hand side is actually equal to a situation where we have a CFT with some boundary condition here at the boundary of the CFT2 with some quantum mechanical degrees of freedom. So it's sort of like a D-brane with some degrees of freedom that interact with each other. With the interaction, it's not quite conformal, but nevertheless will allow us to well, to define some kind of boundary state, and the dual description is this one here. Okay, and this model is certainly can be viewed as a limit or as approximating the dynamics of certain four-dimensional black holes. For example, magnetic black holes in a theory with a large number with massless charged fermions lead to exactly a situation like this, where the CFT2 consists of a large number of two-dimensional fermions. Now, so that's a model that was discussed in detail by Ahmed in the previous talk. So now we'll discuss almost identical model, which is just the same model, but in Euclidean space. So this is exactly the same model. And what was space before, we will think of that as Euclidean time. And what was time before, we'll think that as being space. Okay, so we just, first we did a Euclidean rotation of the previous model, and then we just changed what we are calling the direction of Euclidean time. Okay. So again, now in the past, we have Euclidean ADS2, or otherwise called hyperbolic space, with dynamical gravity. And then here in the future, we have flat space with no gravity, and we have a CFT2 with transparent boundary conditions. And that can be viewed as a CFT2. And the black line here is some boundary condition plus localized and interacting boundary degrees of freedom. That defines some kind of state, some kind of boundary state for the CFT2. So we can think of B some particular state in the CFT2. B ends up being a non-normalizable state in general. And then we just evolve that in Euclidean time. That gives a well-defined physical state. So if we evolve it, so that by some amount of Euclidean time here is denoted by the width of this yellow region, we get a well-defined state here in this region. So first we'll study this model. It's simpler, but we will also see that even already in this model, there is a kind of cosmology also. So first we'll compute the entropy of some subregion. So let's imagine we have some interval here, and we compute the entropy of this. Now, if we look at this problem, the state of the quantum fields here is basically the same as the state of the quantum fields in Minkowski space, because we can just remove the overall factor by conformal transformation. And then the entropy is just the naive entropy, which is C/3 log of the length of this interval times some UV cutoff. Don't confuse the epsilon UV with the epsilon infrared, which is the cutoff here that was discussed also in the previous talk. Now, what happens when A is very large, when the length is very large, then okay, so there is, okay, maybe I should come back here, went too fast. So when L is very large, this naive entropy diverges, it becomes very, very large. And it seems to contradict what we expect from this picture, because here, when this interval becomes very large, the state that we have here is a state which has somehow a finite amount of entanglement. So the entanglement might get created by these degrees of freedom that are sort of propagating, if you wish, along Euclidean, along this Euclidean direction. But the amount of these degrees of freedom is roughly S0, roughly the number of these degrees of freedom. So S0 is just the topological entropy of this two-dimensional region, the extremal entropy. And so that there seems to be a contradiction when L is very large, but let's see what happens. So when L is very large and we insert some twist operators, we can have some cut here, and the cut, of course, can be moved into the gravity region. And once it's in the gravity region, we can imagine splitting it by applying the island formula, which tells us that we can split such cuts and create sort of then emergent twist operators here, which cost some term proportional to the area. So here, each one will give a factor of S0, and then the value of the remaining dilaton on each point, and then the semi-classical entropy of these two regions. And if the interval is very large, this is the sum of two separate semi-classical entropies. And now we should extremize this over the position of this endpoint. And when we extremize that, we find that so we should extremize the function. There is a very explicit function So this piece comes from the behavior of the dilaton in this region, and this other piece is just the standard entanglement entropy of an interval. That's the top, and this is just some simple factor that comes from the fact that there is a warp factor in this region, so from the conformal anomaly. Anyway, so a very explicit function. You can extremize it, and you get the value of C where this position is. And this gives some particular value of C that depends on the form of the asymptotic form of this dilaton, and so on. So, okay. Now, of course, in order to see whether this is the global minimum or not, you can calculate the difference between this island-like contribution, which is what was before, and the naive contribution, which is the first expression with the log. And we find an expression like this. And so for very large L, this becomes negative. So that means that the island-like contribution dominates. And that will happen for large L, for large enough L. Now this looks like it's exponentially large in S0, but we can work in an approximation where we will discuss always in the rest of the talk and in what I've discussed so far, an approximation where we take C to be very large, and phi r over L very large, S0 very large, but with these ratios fixed. So there is some limit where somehow all the number of fields scales as the extremal entropy. And in that limit, the advantage of that limit is that we can neglect the quantum mechanics of the boundary graviton. If you don't know what it is, it's not important for the talk, but if you know what it is, you can rest assured that we don't need to include it. And then there are various minima because this point can be really into the bra region of the state or the ket region and so on. So, so this result looks qualitatively reasonable. It is saying that the entropy of the interval cannot be bigger than essentially 2S0. And this is roughly what we expect for a state with bounded long-range entropy. So at this point, we can be happy. Okay. But actually, these results are wrong in detail. And the entropy obtained in this way does not obey the strong pseudo-additivity condition for a certain choice of regions. And I guess I have time, so I'll discuss this kind of paradox again. So, okay, so why does this formula fail? So this transparency might be a little technical for some people. So but rest assured that the message of this transparency is that there is a problem. And I will now explain in detail what the problem is, and then we'll discuss the solution. But you don't need to understand the problem in detail to understand the solution, okay? So the idea is to consider a system which contains a large number of fields, so plus one extra matter field. So the total number of fields is, if you wish, C plus 1. So, and then what we are going to call region A will be this spatial region, but considering only C fields. And then region B will be the same region, but considering only the extra fields. And the region A union B is considering that same spatial region, but both fields together. Now, this is a region here where we have flat space, and there are no gravitational interactions, so it's consistent to think of these two fields as totally decoupled. Of course, when these two fields live here in the gravity region, they are really coupled through gravity, but they are not coupled in this region. So we can use, the regions are well defined, and the state might be entangled across the two fields and so on, but the definition of the regions is correct. The definition of the subsystems is correct. Okay, and now we'll also consider the region B complement, which is the region outside the interval, but only for so the region outside the interval, but only for this single extra field. Okay. So now we compute the following. So now we have the entropy pseudo-additivity condition. So that involves 3 regions, and we can choose those 3 regions to be A, B, and B complement. So those are the 3 regions. And we have the standard entropy pseudo-additivity inequality, which is a pseudo-additivity inequality that should always be obeyed. Okay. So now we have the entropy of A union B. So that's all fields together here. And that we have the usual island formula, the one we had before, which says that the entropy is S0 plus some number multiplied by C. Okay. Then we have the entropy of A union B complement. And that's the entropy of all the fields, these extra fields here, But these fields are basically will be in the vacuum in this approximation, so that the entropy will be essentially 0. Then we have the entropy of A union B complement. So we have the global state here for B, and now we are considering also the fields in A. Okay. So now when we do this business of so now there is something interesting here, which is that when we put the twist operator at these endpoints, because we're considering all of B, the twist operator is only the twist operator for the fields in A. Okay, that's what we have in the top boundary. But when we have the emergent twist operators that appear here, because we're in the gravity region, those emergent twist operators affect all the fields equally. So both the field, this large number of fields plus the extra field. And so what that means is that after these fields emerge, there is here an extra, there are the twist operators for A that, well, then will give us the same answer as before. But then there's the extra twist operator for B, which will give us the entropy of essentially this interval here. And that will go like logarithm of L, okay? So sorry, it's this piece here. And then also similarly, when we compute the entropy of just purely B, we'll get some answer, which will be again C log B, okay? So then the net result is that this first term cancels against this other term here, and we get two things that go like log L that increase with L, and so we'll have a contradiction with this inequality, okay? So that's the contradiction. So
one quick question: is the B fields just one field, or is it C?
Yeah,
field?
one field. Yeah.
But in SB,
one field.
you have
The B fields is just only one. Yeah, C is very large, and well, maybe in some of these terms there is C plus 1. But as we said before, we are always taking very large C.
In SB, there is C log L or just log L? Sorry.
Sorry. Yeah, this is a mistake. You should be log L. Yes.
Okay, thanks.
But it doesn't matter. I mean, there's this piece. Yeah, there's only, sorry, none of these two terms should have the C. It should always be just log L. So there is only a 1 times log L.
Okay, thanks.
But this growing piece is what causes the problem. Okay.
Thank you.
Sure. Okay, so if that result was wrong, why are we talking about it? Okay. So just to show you that the previous discussion is incomplete and that some new idea is needed. Okay. And the new idea is that there are new contributions to the density matrix, the so-called bracket wormholes. Okay. And something similar was pointed out in the paper by Pennington, Schenker, Snuffer, and Young in the context of a simpler toy model. So the idea is that when we this picture here represents the time evolution, the Euclidean time evolution here of the bra and the cat in the yellow region. And we are tracing it. So we're calculating trace of rho. So that's the bottom calculation, trace of rho when even we don't have any interval. And the idea is that there is a new space-time geometry which connects the two sides that is important for doing this computation. Okay. Now, what is this geometry? So this geometry is essentially the same as the two-dimensional eternally traversable wormhole that we discussed with Xiaolan and Qi, which is in turn based on the idea of Gauss-Jeffreys and Wall. So Gauss-Jeffreys and Wall show that when you introduce interactions on the two sides of the thermal field double, you can make the wormhole traversable. This is simply saying that if you introduce interactions which are present for all times, then you get a rather simple time translation invariant. In this case, is invariant along this spatial direction. So this is purely Euclidean. And so here the interaction, so here we can think of somehow two quantum mechanical models which live on this edge and on this edge that are interacting with the CFT, and that we are summing over the degrees of freedom of the CFT. So that induces an interaction between the two quantum mechanical models, and that then is responsible for creating this wormhole. Now, in order to solve the equation, so this corresponds to a completely explicit equation, and the way this equation works is that there is a circle here. There is effectively a circle, and therefore there is some negative Casimir energy for the quantum fields, and this negative Casimir energy produces the traversable wormhole. Okay. And you get an explicit profile for the metric. The metric is essentially the metric of the strip of Euclidean ADS2. And then we have some particular profile for the dilaton. This profile for the dilaton has the, I will not give its explicit form, but the basic feature is that it's symmetric around sigma equal to 0, so this central point of the wormhole, and it grows in both directions when you approach the boundary here, this green line. Okay. Now it's interesting to think about the Lorentzian interpretation to this. So we were discussing the state as a way to prepare in a state, and then we can evolve in Lorentzian time. So we can cut along this blue line. If we cut along this blue line, then we get the state in the CFT that looks thermal. So in this approximation, it looks like a thermal state, and it's thermal because we have a Euclidean circle over which the fields are evolving. Okay. And there is some effective temperature that depends on the parameters of the theory. Now, note that from the holographic point of view, so from the point of view of these two boundary states, the state cannot be thermal, it must be pure. Okay. Now, when we do this cut here along the blue line, we could also cut along the dotted blue line, which it's on the other side of the cylinder. So the blue line without dots, it's in the front face of the cylinder, and the other one is in the back face of the cylinder at sigma equal to 0 in the gravitational region. Now, when we cut here, and then we go to Euclidean time, I mean, this is a point of space reflection symmetry. And when we go to Lorentzian time, point of time reflection symmetry, we get a metric which looks like this. So previous metric had a cosine of sigma, now we have cosine of eta. And it's a metric which shrinks as you go to either very large or very negative eta. And the dilaton also, once you put in the eta, so the form I didn't give before, here I'm giving you now the form in Lorentzian time. And it's a form that, again, goes to minus infinity as you approach eta going to infinity, which are the singularities of this collapsing universe. So this is a metric of a collapsing universe which expands from a singularity, reaches a maximum size, and then collapses again. So we have a situation, so roughly, so here we're saying the same thing, but in a different picture. So we have a situation where we have, let's say, a circle in the CFT, and then we have this period of Euclidean time that is what we were evolving the CFT with. And here we had some boundary which has a dual, which is this space-time geometry, this spatial wormhole, Euclidean wormhole. And then it joins with this other universe, closed universe, where things shrink to 0. Okay, and this is the dominant configuration when L is sufficiently large. So this is what it means to be sufficiently large. Now, turns out that when the I-line contribution dominates, which is what the previous one we said, actually also the full space-time wormhole should be the full background geometry over which we can do those computations should be this type of wormhole. So that happens for when this capital L is large enough, and then the whole computation should be done with this on this geometry, and then in that case the island actually lives in the other side of the cylinder. So we have the island in the, let's say, the actual definition of the region is the red line. And the dotted red line is some island that lives in the other universe, okay, in the closed universe at the t equal to 0 spatial section. And we also find that this entropy saturates at about 2s0, which is what we expect. And this has no stronger additivity problem because in the semi-classical description, these two states are two states that make sense in a semi-classical theory, in the theory of the quantum fields living on this geometry, and therefore will not have any additivity problem. Okay, so in other words, for very large L, so when the bracket wormhole always dominates, and the entropy behaves like this for intervals of different size, so we have some slope here, that's when we don't have an island, and we have something that looks like a thermal entropy rising with the proportional to the effective temperature. And then when we reach some maximum, we have some constant of around 2s0. So essentially this entropy, and then it decreases again. Now, maybe one way to think about this is that if the naive picture of this hyperbolic evolution is that it would give us infinite, so we have a semi-infinite interval, it will give us an infinite entropy when we would give us an infinite entropy. And a tensor network picture would be something like this, where we have the tensor network producing the state, and we're cutting an infinite number of lines, and for that reason we get some infinity. I mean, it's a logarithmically divergent infinity, but it's still infinite. And the way this, and this seems to be in a bit of contradiction with the interpretation of the finiteness of entropy. And the way it gets fixed is not by fixing the geometry here, by cutting off the geometry here, but is fixed by, in some sense, we cutting off the geometry, but only after we compute the density matrix, we get this new geometry, which has this finite circle. And the tensor network picture would therefore have finite depth. So we have two sides because we have the bra and the cut, and we are identifying and summing over the indices over this region, and then we get the finite size geometry. So we had this picture where we had an interval, and then if we understood the state of this interval, then the entanglement wedge, of course, includes also this island, and this region in the closed universe. And of course, if we consider the full state on the full CFT, we also have, are describing, I mean, we also have a contribution. Yeah, maybe I should be more slow here. So if we computed the naive entropy here, we would get something large, which would be the thermal entropy on this interval, on this circle. But the island formula tells us that we should also include this closed universe, because the fields here in this region are entangled with the fields in this closed universe. And then when we apply now the RT formula to this situation, including with the island prescription, we get that the total entropy of the quantum fields here is actually 0, because the full, it's 0 because we are obtaining the state, but these two are linked by Euclidean evolution, and so we have a 0 entropy state. I hope it's clear from the picture. It's for the same reason that the thermofield double state, for example, has 0 entropy. Okay. So the conclusions of this model are the following. So we consider the gravity dual of a particular non-conformal boundary state of a CFT. For large circles, we produce a state which can be interpreted as coming from a bracket wormhole. And in the semi-classical description, we have a thermal state on the CFT circle, which is entangled with a closed universe. And the closed universe cosmology is an entanglement wedge of the full state in the CFT. And so you can say that in this way, we can describe this closed universe as part of the complex state of a CFT. And I should say that this is very similar, very analogous to a black hole that forms and evaporates completely. In that case, also, we get some kind of cosmology. You can say the cosmology is the black hole interior, which is entangled with the outside radiation. So this toy model is not really conceptually very different from what was discussed previously by, involving black holes that form and evaporate. So now, so after understanding all these details of this model, we move to de Sitter. So the short story is that something similar happens. So it's very similar to this model that we just discussed, but there are some caveats in the word similar. And the final picture is a little strange, so we welcome your criticisms. The picture is somewhat similar to the one in Pennington, Schenker, Stanford, and Young, but their toy model doesn't quite apply when we have propagating fields. So, so the simple cosmological toy model is what we discussed before. So this is the same transparency that we had before. I'm just reminding you. We had de Sitter and then flat space gravity. And again, we can compute the entropies of subregions. So we have a subregion here. We can compute its entropy. We get the naive answer. this computation is identical to the one we had before. It doesn't matter for that, for the purposes of this computation, that this is Lorentzian versus Euclidean evolution. In both cases, the standard Bunch-Davis vacuum, or yeah, the standard Euclidean vacuum, if you wish, of the sitter, or the sitter invariant vacuum, in this context is just simply the state in flat space, the same state as the Minkowski vacuum for the conformal fields. So that's special, of course, for conformal field theory. We are assuming the fields propagating in this background are conformal. So in that case, we get again this answer, and again, when L is very large, okay, we don't have some that this is equal to some. In this case, we don't necessarily have a boundary dual in the sense of ADS or DS-CFT duality. Maybe we have it or not. We will not make this assumption. We will just apply the RT formula and really try to see what the RT formula is telling us. Okay. As in the Euclidean case, we will have these island-like contributions. So when we compute the state using the in formalism, we have the evolution of the ket, and then we have the evolution of the bra, which goes backwards in time. Here we've drawn it here up here, but this is really an in computation, if you know what that is. And again, we can try to look for islands. And we essentially, so we try to look for these islands, and we essentially get the same answer as in the Euclidean ADS case. So the behavior of the dilaton is similar and so on. Now there is one subtlety, is that now the dotted line here is along a time-like direction. So when we have a twist operator inserted here on the top and a twist operator here inserted on the bottom, those twist operators are separated along a time-like region. And the way we defined this was to first compute the twist operators for space-like intervals, and then analytically continue them to time-like intervals. And that process produces some i's in the twist operators and some extra i's in the entropy. But when we sum, so over, so there is some I when the island is in this configuration, there is some minus I when the island is here on the top. So when it's in the ket, on the one island, when the island is on the bra, we have one I. We have the opposite factors of I when the island is on the ket. And one could imagine that these i's cancel. And then we get some real answer for the entropy. However, that answer has the same subadditivity paradox. I mean, the elements are identical to the ones we discussed before, and again, we have the same paradox. So we have a problem with this idea. So the idea is that now that problem will be solved by, again, bracket wormholes. Now, what are the bracket wormholes in this case? Okay. In order for us to, so it's some geometry, the idea is the following. So we have the period of flat space evolution here, the yellow region. Here we're evolving in Lorentzian time, so to some final time, and then backwards in time to the reheating surface. And then we are evolving here again. So this is now a Lorentzian evolution to the past, and we're imagining there will be some period of Euclidean evolution, and then some period again of Lorentzian evolution in the ket. So the period of Euclidean evolution is supposed to join the bra and the ket. Okay. This is somewhat similar to the Page's discussion of forming a thermal density matrix, or getting a thermal density matrix for cosmology. Yeah, so here the geometry, so that's in general the philosophy, what I just said. Now we're going to look here at the very specific solution, where we take the metric to be minus d tau squared plus inch squared tau dx squared. So this is, for those who know, this is just the metric of ds2, two-dimensional de Sitter in the mean coordinates. But here x could be compact and have some length L. So we have this geometry, will have some singularity at tau equal to 0. And then the dilaton has this form. So we are again assuming the fields have a zero stress tensor. So if we take this geometry, then we take a contour which so there's one more point I should say is that we're going to interpret. So there is the tau plane that we're going to do a deformation in the complex tau plane, and the deformation is the following. So first, the contour in the complex tau plane is the following. So we go along real tau, where we look like we have a collapsing cosmology. And then here we have an expanding cosmology, and we have some singularity at tau equal to 0. And we are going to go around the singularity in Euclidean time. So this going around the singularity in Euclidean time is related to the Euclidean evolution that we normally do when we do Hartle-Hawking-like things, or let's say the page prescription for the density matrix of the universe. And this piece, which looks like a collapsing universe, we are really interpreting it as really coming from the Bragg contribution. So really here time, we are imagining that we are simply evolving backwards in time from the final time to some early time, and then we do the Euclidean evolution joining the Bragg decade. Now, if we go to conformal time, so if we go to the conformal time direction, so we have this expression for the conformal time, and in conformal time, this contour really looks like a thermal contour. So we go back to some early time, then this is just the usual Euclidean thermal contour that we use for Euclidean thermal field theories. So this prescription and the geometry itself is very similar to the double cone of Saad, Schenker, and Stanford. They also had a geometry which had a singularity, and it had two sides, and connected these two sides and so on. And there was some prescription for how to go around the singularity. So it's very similar to their story. But well, it's arising in this type of cosmological interpretation. Now, it turns out that, so that what I described before was some kind of contour. I just haven't given you a solution yet. And when we try to look for a solution in this problem, we can basically solve first the gravity equations and then try to find the solution for the dilaton. And when you find the solution for the dilaton, there is one parameter that appears, which roughly speaking, you can think of it as the effective temperature. So effective temperature is the temperature that we will see in this yellow region. Okay, so after let's say, imagine we find the configuration, the temperature, so there are a variety of off-shell configurations with different temperatures, and they contribute to the action in the following way. So there is a gravitational contribution, which actually cancels because it's purely imaginary. The fact that it's purely imaginary comes from the fact that it comes purely from the boundary graviton. And the boundary graviton here, it lives in the purely Lorentzian region and gives a purely Lorentzian phase, and that phase cancels between the Bragg decade. It is different in the Euclidean case that gave a non-zero contribution that depended on T effective. But then there is a CFT part, which comes from, well, there's a Lorentzian evolution which cancels, and then there is a Euclidean evolution which doesn't cancel and gives sort of some answer which is similar to what the partition function of a conformal field theory at that effective temperature. And this then, so this effective temperature is just the off-shell parameter of the solution. So due to the gravity cancellation, this temperature is actually driven to infinity. And as opposed to the Euclidean case, the case we discussed before, here we have something that is not a solution. So this effective temperature is driven to infinity. And the bottom line is that we think that this is actually the right answer for this system, that's what this theory actually does. So that's why I said that the answer looks a little weird. Now, to gain a little more confidence on this, so we will take this state that we get in this way, and then do a little bit of Euclidean evolution. So after we produce the state at this final time at the middle of this yellow interval, we will do some extra Euclidean evolution. So that extra Euclidean evolution can be viewed as applying a projection operator, which projects the state that we're getting, which is a somewhat singular state with infinite temperature, to a state with lower lower temperature, okay, lower energy. And when you do that, then that actually gives a wormhole of the type that we discussed with a finite effective temperature. And what happens in that case is that the matter contribution has two parts. One comes from the Casimir energy, and the other one comes from the conformal anomaly. So two contributions to the energy. They both look somewhat similar, and the two cancel out in this particular configuration, and then you get the solution we discussed previously. So the contour and so on that we discussed previously. And so this is something you can do. Another thing you can do is you can modify the dilatant potential. So so far we've been talking about JT gravity, but you can modify the JT gravity appropriately. And then in this case, it's not necessary to evolve into Euclidean time in the future. But of course, always we're evolving to Euclidean time in the past. And it's a slightly more complicated solution that we are not going to discuss. But also has a finite wormhole. Okay, so in the previous discussion, in the previous example, we had a state in the CFT entangled with a closed universe. Is there something similar in this case? Now, in this case, we can have this contour that we discussed here. And in the previous case, that in the middle of the contour, we found the collapsing universe. And here something similar happens. So if you come here to the middle of this wormhole and continue this in the imaginary tau direction, so you call t equal to IT, then here we get the geometry, which the term in brackets looks again like a collapsing universe similar to the one we had before, but we have an overall minus sign. Okay. So if we could ignore this overall minus sign, which if the matter fields are a CFT, then we could think that we could ignore this minus sign because the matter is conformal, so the overall conformal factor doesn't matter. So if we can ignore this minus sign, then we get a similar behavior with a collapsing universe. If we say, well, I don't trust this argument that you say you ignore the minus sign and so on, I take the full metric, including the minus sign, then that metric is the metric of the static patch of the sitter, and t would be a space-like coordinate, the radial coordinate in the static patch, and x would be the time coordinate. But so there, the physical interpretation is a little less clear, especially since we are taking x to be compact. But so it's a little more clear if we instead take the first interpretation that we were suggesting, which is the one where we do not ignore this minus, but where we ignore the minus sign, and then we have a geometry which again looks like a collapsing universe, and then we get a picture very similar to the one that we discussed before. Now, if we computed the wave function, so there is here some discussion about exactly which connected contribution should we include or not. So if we compute the wave function of the universe, so we could sum over universes with no boundaries. Now, after we do the trace, some partial trace, then even if we were summing before with universe with no boundaries, it seems reasonable that we should connect the Brand-Dequette, that we should really include these geometries that connect the two boundaries. This was clear in the Euclidean case, and I think for the same reasons we should include them in this case. There is a little puzzle, which is that there are also solutions for typical pure states also, because you can take this thermal state of the propagating along the cylinder, and you can consider it just one typical pure state out of the whole thermal ensemble, and that will have also the same characteristics, the same typical energies, and so on as that we had before, and so that will lead to a puzzle similar to the puzzle that fields are discussed early this morning. So I don't have anything to say. I just mentioned that it is present in some way here. I think if we are doing traces and so on, which is what we were doing in the beginning, then we don't have to face this puzzle that is pointed out here in point number 3. And I should emphasize that also in the cosmological case, it is very natural to take a trace because or to connect the Brand cat because we are computing, we are ignoring what will happen to our future. And also we don't observe things that are very far away from where we are. So it is very natural that in actual observables that we do in cosmology, that we observe in our real world, we are in some sense, even if we had a wave function of the universe, which is in a wave function for the complete slice, we would be tracing out over regions where we don't make observations. And that certainly, I think, is a strong argument that we should consider this bracket wormholes and these connections that we could have had in the past. Now, I should say that these bracket wormholes are very closely connected to bounces, the bounces that people like Steinhardt and others have been discussing. So we have this Lorentzian time evolution, and we said that this shrinks to 0. So this could be a circle that shrinks to 0 size. And so we have some singularity. So we have something which looks like a singular universe, but the idea is that we can give a non-regular wave function. Well, it wasn't quite regular in this explicit example because the temperature was driven to infinity, but there are small variations of this where it is actually regular. But the interpretation is quite different. So we have in the bouncing universe interpretation, this was a physical universe that was collapsing to 0 and then expanding. Now in our interpretation, this collapsing universe region was equal to the expanding universe region. I mean, it was just the bra of the ket, which was the evolution, and really we avoid the singularity by going into Euclidean time. Okay, and actually the full contour when we trace over the future is actually a circle, so it also could be viewed as a cyclic universe, but with a new meaning of what we're really doing. So it's not the same as the cyclic universe idea of Steinhardt and Turok, but there's still a cycle. But the cycles between the bra and the cat. Okay, in conclusions, we've discussed the need to include a bracket wormhole in computing some cosmological observables in the context of some very specific toy models. The state continues to be pure, but it looks thermal in the semi-classical gravity description. It can be both thermal and pure because there is a presentation where you view it as entangled with another, the Sitter case somewhat unphysical collapsing universe, and then the fine-grained entropy formula would tell us that it is pure under these circumstances. And also in this interpretation, the Sitter entropy appears as the maximal entropy for an interval. So we have an interval in this two-dimensional case. That's how the Sitter entropy is appearing. It is manifesting itself. The fact that the Sitter entropy is finite has as a consequence that the entropy of an interval is bounded. So this is a manifestation of the Sitter entropy in, let's say, cosmological observables or in the cosmological wave function of the universe at late times. Okay. So it gives a kind of, there is a UV computation that you can, a well-defined computation we can do to calculate the Sitter entropy. Now there are many questions, so we concentrated on the 2D case. It would be nice to extend it to higher dimensions. I think some aspects probably can be extended. And maybe after understanding this appropriately some more features, maybe it could be perhaps applied to our cosmology in some way. Okay, thank you.
Okay. Thank you, Juan. So, questions, comments?
Hi, Juan, this is Samir here.
Yeah.
Can I just ask a question about general cosmology? So in the FRW phase of your model that you had started with,
Mhm.
could I ask the question that people have asked about cosmology many times before? Like, just imagine that to be a low density dust phase or something.
Mhm.
And then if I take a larger and larger region of, let's say, a flat cosmology, I can look at a ball-shaped region and find for a large enough radius of that region that the entropy in that region can be just the matter entropy, can
Yes.
be more than, for example, the area of that region, because it's
Yes. You can definitely ask this question, and the entropy will behave as I was showing in some previous transparency. It grows as the size becomes larger. Then it will saturate at twice S0, which is equal to the zeta entropy.
Right.
And then yeah. So
good. So that's what I was curious about. So now I'm in the FRW phase. So I'm not actually don't have the de Sitter horizon, but a growing horizon. And if I have like dust particles in there, each one has a spin half, I can manifestly see that I can actually have an entropy which is unbounded. It's directly in the spins of the quanta. So in fact, I could make a state which is entangled with spins outside. I guess you're saying that's not the state I have, because you're taking the Hartle-Hawking initial condition. Is that what you're
Yes. This whole computation is for a particular state that was prepared with the Hartle-Hawking initial condition.
I understand. Okay.
Yeah.
Thank you.
Yeah. I've also separated a piece where the cosmological evolution into a piece where gravity was important and a piece where gravity was not important.
Right.
So that was the green versus yellow regions.
Right. Okay. Thank you.
Yeah.
Any other questions or comments? Stan, you've got your hand up.
Yes.
Wait, Stan, we're not hearing you.
Yes, excuse me. I'd like to ask the question regarding the point you made about this, the relation between the thermal and the fact that you have the state that is pure, but it can appear thermal if in the semi-classical approximation.
Yeah.
Is it correct? Am I understanding correctly that the fact that the state appears thermal is due to the semi-classical approximation? If one were to go beyond it, it would appear pure?
Yes. Yes.
Oh, yeah.
Yes.
So it is the corrections to the semi-classical gravity.
Yeah. But this is non-perturbative corrections that involve non-trivial geometries.
Oh, of course. Of course.
Yeah. That's the same as in the story that in what Ahmed discussed. The same principle.
Thank you so much.
Any other questions or comments?
I had a question about this gluing. So, I mean, I've seen that, there's this gluing going on between, the de Sitter region and the flat space and anti-de Sitter and the flat space.
Yeah.
As a solution, when you do that, you get some problems. You need to put something there, some wall or some boundary conditions or something to take over the profile. I'm just wondering if anybody has thought about some model to build this in one theory and, solving the same equation on both sides. Because there are some junction conditions, for example, if you just put flat space here and de Sitter here, there'll be some junction conditions and you get some tension and you get some domain wall between them. It's hard to get a continuous gluing of flat space with some other space.
Yeah, so I guess you should think of this as a limit of the standard inflationary discussion, where we have a period of de Sitter, nearly de Sitter evolution. And then when the inflaton gets to some value, you transition into, let's say, imagine you have a quick reheating, and then you transition to flat space, or not flat space, but FRW. But you're imagining that FRW evolution is much slower than the previous rapid expansion. That's what this model says. If you want a more technical answer, you can, in the context of JT gravity, you can tune the potential of the dilaton in such a way that that potential is linear for some range of phi's. And when it reaches a particular value of the dilaton, it becomes constant. And then you have a transition between de Sitter JT gravity and flat space JT gravity. So in that example, we would, depending on when the transition happens, as it happens later and later, the actual final value of the dilaton will be larger and larger. And so the flat space theory will have a finite coupling. It will not be, yeah, it will still have gravity, but it will have a Newton constant, which will be very small and can be tuned to be smaller and smaller as you take this cutoff later and later.
In this transition, are you imagining that the whole universe goes through the transition uniformly at once, or is this something where you can form bubbles? Or
yeah. So here, in principle, there are fluctuations, quantum fluctuations that are related. Well, this model is not quite an inflationary model in the sense that there is in ordinary inflationary models there is an actual physical clock, which is the inflaton that can have spatial fluctuations. Here, the dilaton is not quite a dynamical field, right? It's really, you can choose a gauge where it's completely constant. And so in that sense, it's not quite the same, but there could still be some fluctuations associated to the boundary gravity mode, and we have ignored them. So we have ignored the fluctuations generated by the boundary gravity modes because we were working in a very specific limit of large C and so on. Yeah, there are many questions of this kind that will be more relevant if we wanted to go to higher dimensions and so on.
Right.
But
okay, any other questions or comments?
I have a question.
Go ahead.
Just in the answer to the last question, you said that you can think of the process as a limiting procedure where at every step, actually, you have a Newton's constant turned on in the flat space Newton. In that case, how does the Hubble scale compare to the scales that you're exploring when you're asking about these intervals? And do you get a separation of scales as you take G Newton to 0?
Yeah, now I suppose when you ask about the Hubble scale, you're asking about the Hubble scale at the end of inflation, right? Compared to the size of the interval at the end of inflation. Is that the question?
Well, at whatever time you're going to be choosing your interval to lie.
Okay, so the final interval is at
finite density.
Yeah. Well, let me first answer a simpler question, which is that the Hubble scale at the end of inflation is much, much, much smaller than the size of the interval, right? And in the limit, it goes to 0 compared to the size of the interval, right? Now, when we consider an interval, of course, there is also the Hubble scale of when that interval entered the horizon, okay? That of course, will, well, if we go backwards in time, there is a time at which the comoving scale, or the x coordinate of the interval, at some point is within the horizon, right? Sometime into the past. I'm claiming that when we have a very large interval, right, then at that time we don't trust the sort of standard single copy solution. We have to transition to this bracket wormhole.
I think I'm asking a simpler question, maybe. I'm just asking how I should think of the Hubble scale at the time when you specify this interval. Is the Hubble scale much larger than this interval, much smaller than this interval?
Okay. I think I now understand. Yes, your question. Yeah, so at the time you specified is much larger because we are assuming the universe is not expanding. It's just flat space, right? So in flat space, the Hubble scale is infinite. The Hubble distance scale is infinite, right? Because we were saying that the universe is not expanding.
Right. I'm just, it's not immediately obvious to me that when you approach that as a limit of situations where you have G Newton turned on, that you just get to say that.
Well, it is true in this, well, we can approach it as a limit, and in this 2D case, it is true. I think perhaps you're asking me, well, give me a 4D model and where this happens and so on. I'm not giving that to you, but in this 2-dimensional case, this is true.
Thanks.
It's just simply, but yeah, let me see. The reason is that if you just see, these 2D models, the geometry of space is very rigid, right? So it's just determined by the potential of the dilaton. And if we just postulate, if we are free to postulate whatever potential we want, then we can postulate a potential which is linear, right? Which will give us the Sitter solution, and then constant, which will give us a flat space solution. And so after we are in this constant phase, even if G Newton is not zero, the space is still flat, and Hubble constant is infinite.
So the energy density is exact, but you have a finite energy density?
Yes, 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 yes. In these thermal cases, we have a finite energy density. So
if you have a finite energy density at finite G Newton, you can't have a zero Hubble constant, right?
Yes, yes, that is correct in higher dimensions, but that's not correct in 2 dimensions.
Oh, okay.
So sorry, yeah, you can say this 2-dimensional model is not physical, but this is the this is the feature. Of course, the dilaton will evolve, and there will be some maybe analog of. I mean, if you asked about the Sitter entropy, well, I'm not sure what would be the analog. Yeah, if you strictly ask about the Hubble scale, then it's infinite. Just simply because we went to flat space. I mean, it's not. Yeah, this is not something that is possible to. Well, at least I'm not sure how one would do it in higher dimensions. But yeah, so in higher dimensions, if you have homogeneous universes, as you said, you cannot go to completely flat space without having also G Newton equal to 0. In this case, you can. But okay, it's a peculiarity of this model. But I think this is not an essential feature of what I was talking about.
Raphael doesn't look happy, but okay. Any other questions or comments, guys, or follow-ups? Okay. Well, thank you again, Juan. That was really very nice and very grateful. We'll pick it up again at 17:45 Paris time and for the panel. And hopefully Steve Schenker will wake up by then. Anyway, thanks, Juan. And thank you all.